Welcome. In this video, we'll look at the graphs of trigonometric functions in the context of knowing their derivatives. What we're going to be doing is starting with a function that's the sine and the tangent and the secant, and we'll be considering what the derivatives tell us about these functions. So first, let's start with the sine function. So if I start by thinking about the sine function, we always want to think about it in the context of the unit circle. So let's draw a little example of a unit circle here. And of course, we start at an angle of 0, and counterclockwise is the positive direction, and clockwise is the negative direction for our angles. And the sine gives me the y-coordinate of the angle. So the sine gives me the y-coordinate of an angle. Okay, so the first thing we want to do is we want to think about what are the signs of my function. So let's start by summarizing some sign analysis of the sine. Sign analysis is done by creating a number line and indicating the points where the function is changing sign. So notice that the sine value at an angle of 0, so we're going to put our angle on the x-axis. Let's actually use our variable x, because that is the variable that I'm using as my input for my function. And at angle 0, the sine of x, we'll put on the top, has a value of 0 because the y-coordinate at this point is 0. All right, as I go through a positive angle, notice that now my y-coordinate is positive, and it stays positive until I reach an angle of pi. So when our angle is pi, we come back to 0, and in between those points, we were negative. So these were quadrants 1 and 2 in the circle. As I keep going around and get through quadrants 3 and 4, my angle passes pi. I'm now a negative y-coordinate, and so my sine of this angle is negative until I return to the start, which happens at an angle of 2 pi. And so my function will be negative on this region. And I'm going to alternate every multiple of pi. So at 3 pi, I'll be back to 0 and switch to the negative sign. If I were to go in the opposite direction, if I started at 0 and went in the negative angle direction, I get negative values. So I'll be negative until I get to negative pi when I'm 0 again, and then negative 2 pi. And so I'm just alternating sine as I go around the unit circle over and over and over again. So I'm alternating positive and negative. Okay, so that tells me when my function is above and below the axis. The next thing we would do in calculus is to think about the derivatives. So let's look at the first derivative. The sine's first derivative is the cosine function. And thinking again about the unit circle, this is the horizontal coordinate on the unit circle. Okay, so again, we're going to do sign analysis. So I put x values on the bottom of my axis. The derivative, which is the cosine, I'll plot the values that are coming out of the cosine function. Okay, and so again, let's think about the angle 0 on the unit circle. And here I am at x, the angle x equals 0. And notice that my horizontal coordinate, I'll try not to say the x coordinate because x is my angle. The horizontal coordinate at this point is 1. So that's a positive value. And as I go around, I will stay positive until I reach an angle of pi over 2. So at pi over 2, that's an angle, I reach a cosine value of 0. I was positive throughout that region, and going in the other direction, I will return to 0 at the angle of negative pi over 2. So if I go the opposite direction, my horizontal coordinate is 0. Now, as I go past these points, so pi over 2 and I keep going, I'm going to be negative as I go through quadrant 2 and quadrant 3 until I return to quadrant 4. And so that comes back at the angle 3 pi over 2, back to 0, and I was negative in that region. And every odd half multiple of pi, I get back to 0. And again, I'm alternating signs. So when I'm in quadrants 2 and 3, my cosine gives me negative values. And when I'm in quadrant 1 or 4, my cosine gives me positive values. All right. Now, what does this tell me about the graph? The first derivative of a function tells me where I am increasing and decreasing as a function. All right. The third part that we want to think about is the second derivative. So my second derivative, sine's second derivative, is the derivative of the cosine, because that was the first derivative, and that will be negative sine of x. And so this is interesting, that the sine of the second derivative is the same as the opposite of the original sine's sine. Let's summarize that. We've already done the signs of the sine. It changed values, all of the integer multiples of pi. So I'm just writing down all these integer multiples of pi. It goes on forever. That's where my second derivative is 0. Okay. And the sine's second derivative is going to have the opposite sign as the sine. So in quadrants 1 and 2, I get a negative sign, and then positive, negative, positive. What we've done is we've thought about the sign analysis of our function, its first derivative, and its second derivative. And the second derivative is going to tell me about concavity. This function is periodic, so it just keeps repeating over and over again. What we're going to do is it'll be much easier if I think about these signs by going back to the unit circle and considering these number lines wrapping around the unit circle. So if I think about my unit circle, what I'm going to do is I'm going to talk about the signs of the sine function and its derivatives. So we're going to have three values. I've got the sine, its derivative, and its second derivative. And so in quadrant 1, my sine, the y-coordinate is positive. Its derivative is the cosine. So its derivative is the cosine. And that's also positive in this quadrant. And its second derivative is negative sine. That'll be negative. And so what that tells me is I'm above the axis, I'm increasing, and I'm concave down. So let's summarize that by saying positive, increasing, and concave down. In quadrant 2, I'm still positive for the sine. My x-coordinate, the cosine, is now negative, and the opposite of my sine is negative. And so I'm going to be above the axis, decreasing, and concave down. So my graph has a decreasing shape. What this allows me to do is imagine as I'm going around the circle, in each quadrant, I can think about the values of my function and its derivatives so that I can imagine now creating a graph of my function. So between 0 and pi over 2, I know that my function is this is quadrant 1. I am above the axis. I started at angle 0. I'm above the axis, increasing and concave down. At pi over 2, I reach my maximum value. And so I have a horizontal tangent. And I'm going to stay above the axis until I get to pi. Notice that I am decreasing and concave down. That was quadrant 2. Then I change to quadrant 3, and I go until 3 pi over 2. I'll be below the axis. I'll be the below the axis decreasing and concave up. And so I reach my minimum at negative 1 y value. And I am just going to oscillate. That's 2 pi. So that was quadrant 3, quadrant 4. I'm below the axis, increasing and concave up. I did a sign error wrong. I should have been negative, positive, positive. So I'm below the axis, increasing and concave up. And then I just start over because I'm back to quadrant 1. And so my graph reaches a maximum at 5 pi over 2, and then it decreases. And I repeat every quadrant, I change my shape. And this goes on forever. Notice that there's a basic block. Every time I finish one full cycle of the circle, I start my graph over. And so this is where the period comes from. My graph has a period of 2 pi because I start over every 2 pi. Let's repeat the process now for the tangent function. If I have a tangent function as my start, so this is y equals the tangent, and I say what's its derivative, so the first derivative, tangents prime, we know that that is the secant squared of my angle. And it helps to always think about what that is in terms of my basic functions. The secant is 1 over cosine, and so I'm really doing the square of the cosine in the bottom of a fraction. So that's the derivative of the tangent. And the second derivative of the tangent, which we say with 2 primes, would be 2 derivatives of this function. Okay. One way I could do that is think about taking a derivative of the cosine function raised to the negative 2 power. And so this is a composition. I've got a u to the negative 2, that's my y, where u is the cosine, so that I can think about the chain rule. The chain rule would say it's negative 2u to the negative 3. So cosine x is u to the negative 3 times the derivative of u, which is negative sine, because the derivative of cosine is negative sine. My second derivative ends up being 2 times the sine of x in the numerator and cosine cubed of x in the denominator. If I take one sine over cosine and call that tangent, I get 2 times secant squared times the tangent. Although I could stay in terms of sine and cosine. All right. I'm going to summarize these 3 functions that we found, our tangent, our tangent's derivative, and tangent's second derivative, and try to conserve a little space. All right, so now that we have our function and its derivatives, I want to think about what are the signs of these functions, and we're going to do these in each of the 4 quadrants. Let's try this time to do it on a number line. So if I created a number line, I've got quadrant 1, then quadrant 2, then quadrant 3, then quadrant 4, and then I start over in quadrant 1 again, so it just repeats forever after that. And so where do these angles start? 0, pi over 2, pi, 3 pi over 2, 2 pi, and then it starts over. So those are my angles x. All right, so as I think about what are the values of my function, and let's think about the unit circle again. The tangent is the vertical component, what would be y, divided by the x component. And because if I thought about this angle, this happens to be y over x is the slope of the angle. So the tangent of an angle is the slope of the ray. And that helps me think about the sine a little easier. So at the angle 0, what slope does the ray have? The slope has the... At the angle 0, what is the slope of the ray? That ray has a slope of 0, and so the tangent has a value of 0. As I increase, I have positive slope throughout this quadrant. So I have a positive slope throughout this quadrant. And when I reach pi over 2, notice what's happening to my slope. It's going vertical. And so there's a vertical asymptote. So we go to infinity. There's a vertical asymptote at this point. And then I switch to a large negative slope. And at pi, I'm back to a slope of 0. And then I have positive slope again. And then I have another vertical asymptote at pi over 2. And then I'm back to negative slopes. Okay? And so this is the tangent function. It's alternating positive, negative, positive, negative. As I think about its derivative, the secant squared, notice that I'm squaring a value. I'm dividing by cosine squared. So this is always going to be positive except where the cosine is 0. And those correspond to the 2 points where we had our vertical asymptotes. Consequently, when I look at the tangent's derivative, which is the secant squared, it's always positive except at the vertical asymptote. So it's got a value positive throughout these regions, hits a vertical asymptote, then it's positive again. Then it hits a vertical asymptote, then it's positive again. And so what's happening is my tangent function is always increasing. Every interval where it's defined, it's increasing. When I look at the second derivative, notice I've got the secant squared, which we just did at sine is always positive, times the tangent, and we've already done the sine of the tangent. And what this means is the sine of the second derivative is the same as the sine of the tangent. So the tangent second derivative also has those same signs as the original function. Okay? So let's see if we can figure out what our graph looks like. In quadrant 1, I have a positive first derivative and a positive second derivative. So I'm increasing and concave up, and I'm above the axis. Okay? And so what that tells me is that my graph has a shape that's increasing and concave up. And then I have a vertical asymptote. And in quadrant 2, what do I have? I am increasing and concave down. And so a graph that's increasing and concave down looks like an increasing concave down shape. When I get to the angle pi, my tangent has a value 0. Okay, so I cross the axis there. And then I switch and repeat that same starting shape that I am increasing and concave up again until I get a vertical asymptote. And this pattern just repeats forever. So I go up, I cross at 2 pi, I'm increasing and concave up. And so this function, the tangent function, has these vertical asymptotes that repeat. And so the period here is every pi instead of every 2 pi. And I want to just comment, the secant, when I'm at the angle 0, and I say, what's the value of the derivative? Cosine of 0 is 1. And so these slopes here, let me use derivative notation. When I cross the axis, my slope is 1. So I don't cross horizontally, I cross with a slope of 1. I want to wrap up by just talking about the relationship between the secant, the tangent, and the cosine function. So we talked about how we got the graph of the sine function, and we could do the same thing for the cosine function. It has the same shape as the sine function, except that I'm shifted into different quadrants. So the cosine starts at a value of 1, but the shape is the same. It has the same basic period of 2 pi. I want you to notice that the zeros of the cosine function happen on the unit circle when I'm at the 90 degrees up or down. So at the boundary between quadrants 1 and 2 and quadrants 3 and 4. When I define the tangent and the secant, both of these functions have cosine in the denominator. So anytime the cosine is 0, that's out of the domain of the tangent and secant. And so notice that I've got vertical asymptotes for my tangent function. So every time there's a 0 for the cosine, the tangent function has a vertical asymptote. And the secant function will as well. So we talked about how to find the graph of the tangent using the derivatives. Notice that we're always increasing every interval. So from minus pi over 2 to pi over 2, I'm increasing. Pi over 2 to 3 pi over 2, 3 pi over 2 to 5 pi over 2. I'm increasing on each of these basic intervals. And the secant function is the reciprocal of the cosine. So whereas the cosine goes from, let's start in quadrant 1. The cosine function starts at 1 and goes to 0. The secant function will start at 1 and go to infinity. Okay, so as the cosine gets close to 0, the secant gets close to infinity. Once I cross into quadrant 2, I've got a vertical asymptote on the other side as well. I'm close to minus infinity, and I'm going towards negative 1. So I'm going from minus infinity to negative 1, and then I turn around. So I get these cool U-shapes that correspond to the reciprocal of the cosine. And so notice that again I've got vertical asymptotes at all of these odd half multiples of pi. And so these are the shapes of our basic trigonometric functions.